Hi, this video is to discuss and present a full proof of the convergence of Newton's method. This is something we have discussed in class at some point, and in that occasion, I gave the theorem statement that I'm now presenting also here on screen, and I've given you an intuition as to why Newton's method was converging, and in some sense why the theorem was true, but then some of you pointed out that they would have welcomed to see a full proof, and I was obviously very happy of that. And this is my attempt to present this proof. So typically when I present this material, I try to present a proof in a sort of non-standard way. And what I really mean by it is that instead of giving you step by step a set of true statements one after the other, which corresponds to sometimes how proofs are presented in books. I really like presenting proofs, and especially in particular this proof here, by decomposing the method, by decomposing theorem statements, and then offering you a reasoning, or at least a window on what I recall of the proofs and what I can derive of the proofs independently of what's written in books or in my notes. And the main reason why I do that is because in this process, through this process, I manage sometimes to convey a little bit more about what are the mechanisms behind the proof, and I also hopefully contribute to develop the idea that proofs and this type of statement or rigorous statements are really not rememberable by heart. And what one has to keep in mind is a general idea and then work through the statements. This sometimes means that the proofs are longer than they should or they could, and they sometimes are like, if you want, the first long writing about what a proof can be, and then the proofs can be made shorter. But I prefer, for didactic reasons, to go through proofs in this way, at least at the first pass, let's say. Okay, so this is the statement of Newton's theorem. It describes the convergence of Newton's theorem, starting from rather generic assumptions on a function f. So we want a function to be defined in an interval containing the solution. X star in our notation is the solution. And we demand that this function be continuous and with continuous second derivatives. It has to, X star needs to be the root of the function, a root of the function f. And then we assume that f satisfies what we have called in class an exotic condition. And the reason why I call this exotic is because at first sight, it's not clear why this condition is demanded there. So you need to be able to bound f double prime over f prime by a constant, positive constant a. And you need to do that in the interval of definition of the function. So this is a bit mysterious at first, and I've given you an intuition of how these conditions come about, but I'm going to go through it again now. And then the theorem states that if you start, if your initial guess is sufficiently close to the root that you're trying to approximate, so by sufficiently close, we mean that x naught has to be, x naught minus x star in absolute value has to be less than or equal to h, where h is connected to the interval that you started off with, as well as the constant a that you're looking at. So if you start off sufficiently close, then the sequence given by Newton's method converges at least quadratically to x star, and it does precisely quadratically. It converges precisely quadratically if f double dash at x star is different from 0. So when I first read these statements, of course, there are all sorts of subtleties that come about, and that's why I try to go very slowly when I do that, and I hope that my digestion of this proof will be useful to you. Okay, so a useful exercise before I even start doing the proof is to decompose the theorem hypotheses and theorem statements and try to formalize them somehow. So let's revisit them one by one. So what we're going to do is to assume a set of hypotheses. What are these hypotheses? So the first one is that the function f is defined in an interval of width delta containing the root. So let me note it down here. So we were going to basically say that f is defined from a given interval I to R. The idea here is that I is effectively the ball centered around x star with radius delta, where delta is a positive number. And of course, in here, we're demanding that f at x star is 0. So graphically, we are looking into an interval, the real lines. Let's say that that is the solution that you're trying to approximate, the root that we're trying to approximate, x star. I'm not going to draw f in these interval, in this interval. It's actually not necessary. I will just say that this then is x star minus delta. That is x star plus delta. And that's what we call I. That's the interval I, effectively here. So I should perhaps annotate this. Let me do that right now. Here, that is what we call I, and it's the delta of x star. And that's hypothesis 1 done. So I think we have covered up until here. Now we demand further that the function is continuous with continuous second derivatives. So let me just write this down separately. So hypothesis 2, we want f to be C2 on I. And in fact, let me be precise, the theorem statement precisely bunches these two conditions together here. Okay. Now, let me move on further. In here, now we have the existence of what we call the exotic condition. So let me try to restate it. It states something about f double prime of f prime in for any x and y in the interval of definition. So I can now write this down here as a separate hypothesis. H3, pardon. This now says that f double prime of x divided by f prime of y in absolute value be less than or equal to a for all x and y in the interval I that we have. And I think in here it's assumed that a is a positive quantity. We then have a further assumption here. It basically says that x naught is in an interval that also contains a solution, and that this interval has width h. And as I have done this in class, this h is at most D. So it's either, sorry, it's at most delta. So it's either delta or smaller than delta. And the width of this interval is related to is possibly related to the constant A that we have found there. So at this stage, I hope you realize that I am really, I mean, these steps are necessary for me because I have not proved this statement in more than a year, and I'm doing it for the first time, and so I better be careful in all my hypotheses. But I think it's often a good exercise to try and note down things here. I should mention that, by the way, I've forgotten to at the beginning that this proof is, this statement is, and I think also the proof are contained in a book by Suli and Meyer that I'm gonna link down in the description below. So let me just rewrite hypothesis 4. So effectively you start from an initial guess that is in an interval, is a new interval that I'm going to call I sub h. And what this interval is the ball centered around x star, but with radius h, where h is mean, it's either delta, so it's either, you know, either IH is I, effectively, or it'll be smaller than delta and equal to 1 upon A. So in here, we're now having to annotate a new interval, which I will do straight away. I'm gonna go up here, and again, this is purely graphical. And the assumption here will be that x naught is somewhere in here. Okay, let me even change color for this new interval. So I've got I, that's IH, which is BH x star. What we aim to prove, so I'm going to write this now as a claim, is that the sequence xk, where xk plus 1 is obtained with Newton's methods formula, so that xk minus f of xk divided by f prime of xk converges at least quadratically to x star. And also I think that the convergence is precisely quadratic oops, pardon me. Precisely quadratic if f double primed at x star in absolute value is non-zero. Well, that's the statement we are trying to prove. Okay, so I think now I have basically rewritten down everything I think this theorem statement contains, and I will start now with the proof. Now, it's important that you realize that, as I tried to state, I don't remember the proof by heart. And so, and I think it's useful to put myself in this position when I'm proving it to you, so that you can really see how the reasoning works here. So if I remember a little bit about that, so I think just by browsing what is being asked here, I remember a few things. I mean, obviously, there are a few things that are connected to me because I went through this proof once, but really I only have a mind map for what there is to be, what there is to come. In particular, I remember that a fundamental ingredient for this proof, must be Taylor's theorem. And this is pretty much a concept that I've exposed to you already once when I tried to motivate the existence of this hypothesis, in fact. And that's not a hard thing to remember, in that it's natural to use Taylor's theorem when nearby the solution we are demanding some regularity. It's no surprise that Taylor's theorem will be there. And probably the other thing that I remember is that this proof, at least in this statement, for this statement, is a proof by induction. And in fact, what I should be able to prove is that if x naught is in IH, then x naught will remain in that interval, and it'll get closer and closer to the solution, in the sense that the error bound will be divided by half, similarly to what we had done for the bisection method. So I think what we want to do is so we claim, that's how I'm going to do it, so we claim that, I think that's what we're going to claim, that xk minus x star is less than or equal to h over 2 to the k. So that is my statement, and that's true for k greater or equal than 0. And I think that that is what we need to do. But let's say if that were true, it's understandable why we have convergence, right? So we now, this proof is by induction, so I'm going to be calling pk the statement. Well, actually, I can be a bit more synthetic here, and I would say I'm going to call this statement equal to the statement pk. And so I will now proceed with the anchor step. Of course, I mean, in this way, I'm not trying to prove any modes of convergence. So I will not be proving initially that the convergence is quadratic or not quadratic. I will just initially aim at proving that there is convergence. So let's start with the anchor step. The anchor step, I need to prove that P naught whole P0 is true. And I think that is true because by what we call hypothesis 4, x naught minus x star is less than h, and that is h2 divided by 2 to the 0. And so that is P0 being true. Okay. Now, confusingly enough, when we do the proof by induction, and we proceed with the induction step, which is going to be the largest part of this proof, as far as I recall, we need to make an induction hypothesis. So we're going to assume that pk is true, and we're going to show that this implies pk plus 1. Now, what is pk? So we're going to then write down, assume a further hypothesis, which I'm going to call IH for an induction hypothesis. We're going to then assume that xk minus x star is less than or equal than h over 2 to the k. And we're going to prove that xk plus 1 minus x star is less than or equal to h over 2 to the k plus 1. Now, the reason why I spell out these things so pedantically, it's because I want to get a sense for both a new hypothesis that I'm making in this part of the proof and where I want to get. So in particular, from here, this is a good starting point for me to try and do something with xk minus 1 minus x star. And that's what I will start doing now. Okay, so that statement will be about xk plus 1 minus x star, but xk plus 1 minus x star, xk plus 1 comes from Newton's method. And so I can write that by definition of Newton's method as xk minus x star minus f of xk divided by f prime over divided by f prime at xk. K at this point is a generic k. And at this point, what I can do is manipulate this thing a little bit. Well, you know, if I'm honest, the reason why this thing is not, I don't stop here, and the reason why I'm proposing to you to manipulate this a little bit further is simply because in the back of my mind, I know that somewhere Newton's method will have to come up. And so what I would like to appear is a group that multiplies xk minus x star times f prime. And so that there is really no other reason why I'm making this manipulation, except that my recollection is that we need Taylor's theorem. In fact, this is one of the things that I remember. It's one of my mantras that this proof is a direct consequence of Taylor's theorem. So let me write it down like that. I don't know, perhaps I need a name to this equality. Let me call it equality 1. Now, I'm set to use Taylor's theorem. And what I will do then is I'll start expanding the function f around xk. Now, when I do that, well, I'll first do it and then show you why the hypotheses are relevant. Let me just write this a little bit here. So when I'm using Taylor's theorem, I need like a pointer on which to expand, and then I'll just go with it. So I'm going to have now x star minus xk multiplied by f prime of xk plus x star minus xk divided by 2, that's squared, also times f prime times a given number psi k. And there is all sort of comments that I want to make, and I will take it as always very slowly on these occasions. So you may wonder, how come that, you know, how did you pick up, how did you select f of x star here? Why didn't you put f of xk here? The reason why, I mean, it's not so important with the order in which you do it. I just picked it up in this case. It is, however, important to understand what legitimizes this thing. So in here, I could write down by Taylor's theorem, which is obviously correct, but really what I'm doing is I'm using hypotheses H1 and H2 here. So I need a regularity for me to use that statement, okay? I need sufficient regularity, and so that's where H2 comes about. And obviously I'm also using the fact that the function is defined for a next node inside this interval. So we are there yet, still there. So I would say here, CH1 and H2. So we are using H1 and H2 in Taylor's theorem. The other comment that I have to make is, why do I stop at second order? And well, in this case, I got a hint because F was what was in C2, but you can easily convince yourself, not easily, but you can convince yourself that that is at least a good first attempt, because look, in this group here, we have everything that we need. And so that seems a good place to stop. The third comments that I would make is that Taylor's theorem is valid for this unknown number psi k, and this number, it's unknown, but it's what we know is that it's in an interval. And very often when one looks at proofs of this type, convergence proofs about iterative methods, it's immaterial that you do not know what psi k is, because, and I'll get back to that later, because what you really need is just the bound of where psi k exists. The last thing I'll note is that this notation here that I'm using is agnostic about whether x star is greater than xk, meaning that if you read these and think, oh, xk is greater than x star, just think again. In fact, this is an open interval, and you can define it to be whichever is the largest. So this means that the interval xk x star if xk is less than x star, or it means the interval x star xk if xk is greater than x star. Okay, the last thing I'll say is that by hypothesis 1, by hypothesis 2, f x star is 0. That's again by hypothesis 2. Remember, f of x star is a root. So at that point, at this point, you can combine, I think that's what I would like to do. I would like to combine equation 2 with equation 1. Especially, I can see that there is a group at the numerator that really looks like effectively that, isn't it? Yeah, that with the opposite signs now. And so I would now say, by combining, and that is really all I remember, by the way. I remember that I have to use Taylor's theorem and Newton's theorem, and proof by induction. So by combining 1 and 2, we obtain what? Well, we obtain xk plus 1 minus x star equals to what? Equals to a half xk minus x star squared times f double primed at psi k divided by f primed at xk. Oh, let me just bring this factor elsewhere. I can have that. So why does this feel good at many levels? Well, it feels good. I think I'm on the right track, let's say, because in here, I start seeing a group that reminds me of the hypothesis 3, okay? So in fact, this is a sort of justification that I produce often, that's why that hypothesis is there. It seems like that's, you want to have control over these, you want to be able to bound these things. Second, in here, I start seeing something that looks like an error, and at the k plus 1th iteration, and it's related to the error at the kth iteration squared, which is also reminiscent of what Newton's well, of what Newton's method does, effectively. I mean, remember the quadratic convergence thing that I mentioned in other occasions during the course. Okay, so I'm now in a good shape and I can start. Remember what I'm trying to show, because I think you might have lost track by now. We are in the middle of an induction step. We'll have to use the induction step, and we want to show that. We want to show that this be less than h divided by 2 to the k plus 1. So how do I do that? Well, to start off, I will put an absolute value here. That's no problem, I think. And I'm going to start now using all the ingredients that I have. Well, first off, I want to use hypothesis 3. So I think I can write this down now as h divided by 2 times absolute value of xk minus x star squared. And that I can do because, remember, I'm inside I. I'm inside the interval I here. I have this hypothesis here, hypothesis 3. So I can bound that to A. So let me write it down here by hypothesis 3. Then I think at this point I haven't yet used my induction hypothesis, and I can use that straight away by writing this, I think. Let me write first the bound. Just that. And I think that is true because by induction hypothesis, I have xk minus x star less than or equal to h over 2 to the k, and that means in particular less than or equal to h. So in here I can write these as absolute value of xk minus x star times absolute value of xk minus x star, and then one of these two products is going to be less than h. Finally, I can use the induction hypothesis again. And write this down as times h over 2 to the k. There was a factor 2 here. Okay. So when I do that, I obtain partially what I want. And I have a factor that bothers me still. So why I think I'm only partially satisfied, because remember, in here I'm trying to prove that xk plus 1 minus x star is less than h divided by 2 to the k plus 1. And in here I've almost done that. I have this part here that is less than a factor times h divided by 2 to the k plus 1. And wishful thinking would like me to write that. And I think this is legitimate. And the reason why this is legitimate, it's to be seen in what we call hypothesis 4, I think. I'm going to get to that in a second. But look at what hypothesis 4 does. It says that x naught is inside a ball of radius h, and it also tells you what is h and what is its relationship to a. So let me write it here. I'll write it in green so as I will not notate this. By hypothesis 4, we have that. And that means two things, that so you have either H is equal to delta, it's equal to 1 over A. That's one possibility. Or H is equal to delta, but also delta is less than 1 upon A. And the two things combined together means that HA is less than or equal to 1, which is why this further bound was possible. Okay, so again, I am going super slowly here, and I hope I managed to kind of convey all the aspects that of all the hypotheses that are in there. In fact, I'm pretty sure that one could derive even bounds that are quicker than the ones I do. There is probably a better set of bounds that exist, but that's how I remember. I mean, is how I derive them in this instance. Now, at this stage, let's revise where we are. We have just now proved that PK implies PK plus 1, and therefore PK is true for all K. So we have that. So at this point, let me change page, and what we have is that we conclude that xk tends to x star as k tends to infinity. And that is, I can write it down here, because xk minus x star, this error is bounded by a decreasing sequence 2 to the k plus 2 to the k. In fact, h divided by 2 to the k. Remember, there is, this sequence is bounded below by 0. The sequence that bounds above the sequence of error also goes to 0, and therefore xk minus x star goes to 0. Now, we haven't yet proved anything about quadratic convergence, or the rate of convergence, and that's what's coming next, which is, I think, much simpler to do that. But it has a nice little argument that requires some thoughts. So let's see, what's a good place to look at the rate of convergence? Well, I think a good place to look at the rate of convergence, a good bound, is just to recall this thing here. Let me write it down here. So to prove quadratic convergence, or almost quadratic convergence, recall that we have derived this bound here. This was generically, there is nothing, that is just effectively Newton's method plus Taylor's theorem in these guys. And in these, perhaps the thing worth noting is that in this writing, there is only psi k that we have to be a bit careful. We found that psi k was a number bounded below or above by x star and xk. As I stated, I do not know exactly which one is larger, but what we know now is that the sequence of xk goes to x star. So one of the things that we know is that psi k, by the sandwich theorem, will also go to x star. You see, so that's what I'm trying to, this was what I was trying to explain earlier on, that the fact that we do not know psi k in Taylor's theorem and in similar proofs that you perhaps will see later on is not really a big deal, because we can get around it. Here, for instance, we didn't need, to prove convergence, we did not need to know psi k, because we prescribed really a bound that was valid in the entire interval, and so it's immaterial that we don't know psi k here. This passage goes through because psi k is a point that we don't know inside I. So we're fine. In here, you will now see that in what I'm about to write, it's immaterial that we know what psi k is. It's more important that we know that psi k goes to x star. And we can conclude that now because xk goes to x star. And so also psi k will go there. So why I think that was a good bound? Because remember, quadratic convergence was about finding stuff, finding limits of this type, of these sequences. So the error at the k plus 1th term divided by the error at the kth, so that's the error at the kth iterate squared. And very often I've told you in class that very often one does not have the luxury of being able to examine this limit, the limit of this sequence, but rather one does it on the limit of error bounds. Well, it turns out that as you're seeing here, we can perhaps say something directly on this limit because of these of basically Taylor's theorem and of the particular structure of the formula that Newton's method has. So that is now a half absolute value of f double primed at psi k divided by f primed at xk. So the claim that I now have is that this limit is a half absolute value of f double primed x star divided by f primed at x star. And this is something that requires, I mean, it's perhaps immediate, but it's a very easy statement to make without really thinking why you're making it. In here, I'm using several things. The first thing I'm using is the fact, I'm right here, I'm going to write because. First, we have that psi k goes to x star as k goes to infinity, right? We have just argued because of that. And what I then see is that at the numerator, for instance, I've got a sequence of psi k. I'm evaluating f double dash at psi k, and I know that the sequence of psi k goes to x star as k tends to infinity. But that in itself is not sufficient to conclude. I mean, and so does the psi k, by the way, I should say. The same is valid for xk. Also, the xk goes to x star as k tends to infinity. But that by itself is not sufficient to conclude that the limit of the sequence is the sequence of the limit. That can be done, and it's legitimate to do because f primed and f double dash are continuous. Why are they continuous? Well, we have just requested that, I think, by what we call hypothesis 2 here. Let me cross-check. Yes, in H2 we say that f is C2. So I think that's exactly what we're using here. Now, once this statement is true, we can conclude that there is a finite limit to this sequence, and so the convergence is at least quadratic, and it's in particular quadratic if f double prime is non-zero. But if f double prime is non-zero, then immediately you can conclude that this is giving you a number that is non-zero, and so this is precisely the definition of what it means to have exact quadratic convergence. And otherwise, if you find 0 here, you have at most quadratic, at least quadratic, sorry. So this concludes the theorem proof. The only other comments I have is the fact that this statement effectively excludes the fact that f prime can be 0 at the origin. In fact, if your f prime, sorry, it's 0 at x star. If f prime was 0 at x star, then you wouldn't be able to find this bound. This is something that often happens if you try to use Newton's method on functions that have a tangency at x star, so you have a double root. You're not going to experience quadratic convergence, and this has no, it does not contradict this theorem, simply because those type of functions, they do not satisfy f prime. They do not satisfy this hypothesis because you do not manage to find such bound. So I hope I have clarified things rather than confused them. And if you do have comments, let them, you can write them in the canvas or in the discussion below. Thank you.